quickly recall what we have seen last time. So we have our Hodge structure V, well, let's say rational Hodge structure, polarizable, and well, yeah, so we know that this is given by a representation of the Delin torus. And we have the Mumford group. Which is the smallest subgroup, yeah, so it is in GLV, the smallest subgroup over Q, such that so MTV, the real points of this Mumford group, contains the image of rho, the image of the Delin torus. Yeah, and so polarizable implies that MTV is reductive. In other words, this well, this group, it may not be may be non-compact, but it admits a compact real form. So if complexification of MTV admits a compact real form, and we have seen how to construct this compact real form last time. And so I have finished with the following. We have seen that actually MTV is the stabilizer. It's the same thing as a stabilizer of all 0, Hodge classes in the tensor algebra of V, TV. So this is just, so this TV is just the sum of all tensor powers of V and V dual. So in this and direct sum of all such tensor powers, we have some, well, this is naturally a Hodge structure also. And there we have some vectors, the rational vector, so this is a rational vector space. So we have some vectors in this rational vector space that are also of type 0 with respect to the Hodge decomposition. And so MTV in this case is yeah, so exactly the subgroup that fixes all of these 0, Hodge classes. Yeah, so now I have said that I wanted to talk a little bit about this Tanakian point of view. So what we want to do is to well, let's have a look. So in general, well, how to think about constructing some universal Mumford group. So I want to do something like the absolute Mumford group, right? So what does it mean? Something like the absolute Galois group of a field. So well, let's say if we have, so let's think, if we have some sub-Hodge structure. Yeah, so then the Mumford group, so what's the relation between the Mumford groups of V prime and V? Well, actually, one of them projects onto the other, so let's see why. So inside GLV, we have the stabilizer of V prime. Yeah, so this is inside GLV. So the somehow the matrices of the form this upper triangular block, somehow block upper triangular matrices. Yeah, so this piece corresponds to the subspace V prime, and so this is a Q subgroup, right, in GLV. And obviously the image of the line torus is contained in it. So actually MTV is contained inside of this group. But then from there we can go to. Yeah, here I don't. Yeah, right. So yeah, indeed. So in the case of polarized, we can just write that it is a direct sum, but still, so even if it is a direct sum, so I just want to say that one of the groups surjects onto the other, yeah? So MTV will map surjectively onto MTV prime. So why? Because this goes to GLV prime. And of course, the representation, so how does the action of the line torus on V prime? Yeah, so by definition, it's a sub-Hodge structure. So the representation of this line torus is somehow you can factorize as a composition of this map and the projection to GLV prime. So actually, if you restrict this to the Mumford-Tate group of V, it goes to the Mumford-Tate group of V prime. Yeah. Why does it go surjectively? Actually, it's a surjection. Well, because if it were not surjective, then the image would be a Q subgroup of this MTV prime that also contains the image of the line torus, right? So, but this is the smallest such subgroup. So it must be surjective. Well, now we have this. Well, then you may think that we would like to somehow pass to the inverse limit. Well, you know, of all such surjections. But that's not really the rigorous definition. Yeah. So this should be something like the absolute Mumford-Tate group. So how this is done? This is done using the theory of Tanakian categories. So Tanakian categories. So what do we know? So let's, I won't give exactly definitions, but I'll just list some things that we know about the category of rational Hodge structures. We have already discussed basically all these things. So this is the category of Q Hodge structures and their morphisms. Yeah? So what do we know about this category? So first, I want to say that it is it's an abelian category and Q linear. Yeah, so Q linear abelian category. So Q linear means that home space, the homes between the objects are Q vector spaces. All right. What else? It has, yeah, so that abelian means that we have kernels, co-kernels, direct sums, direct products, and the same, somehow finite direct products are the same as direct sums, and so on. So all these axioms of abelian category. But then we also have tensor product. Yeah, so it has tensor product. If we have two Hodge structures, we can take the product. And this tensor product, it has some properties. Yeah, so it is commutative. Yeah, associative it is always, yeah, and also, yeah, so let's just write this down quickly. Yeah, so commutative. Associative, which I will not somehow write down. So usually, if you introduce somehow monoidal categories, with such operation, it is always required that this tensor product should be associative, and there are some, yeah. So there is some pentagon diagram, yeah. So which is the there is a list of axioms that I won't write down. But yeah, so specifically this one is commutative. Moreover, it has a unit, so with a unit. So the unit here is this trivial Hodge structure Q of 0, yeah? And also here we know that the endomorphisms of Q of 0 is just Q, so the base field. Yeah? So the endomorphisms are the one-dimensional vector space. Right, so also we have duality. So we have all objects are dualizable in the following sense. Duality. For any V, there exists V star and some maps. So from this unit into V tensor V star, and from V tensor V star to the unit. So this is just the embedding of the somehow diagonal embedding of the dilations into the endomorphism. So this is the trace. Yeah. So these arrows also should satisfy some axioms that somehow naturally satisfied in this case because this just comes from the structure of a Q vector space. So all these things. Okay, so this means that the category is, well, sometimes people say symmetric monoidal category or a tensor category, and the existence of duality, such categories with this duality are called rigid tensor category. So this QHS is a rigid tensor category. But also there is another piece of data that I want to consider. So there exists a functor from this category to Q vector spaces. The functor called omega, so from Q Hodge structures to Q vector spaces. Just forget the structure, the Hodge structure, yeah, so just the forgetful functor. Forgetful functor. So this functor is called a fiber functor, so omega is called fiber functor. So a fiber functor is a functor of between tensor categories. So let me write it like this. That is exact and faithful. So let's see what it means. So the tensor functor means that it is compatible with all this. Yeah? So it is a functor it's, between abelian categories, so linear, and it is compatible also with the tensor product, meaning that the tensor product of two objects is mapped to the tensor product of the images, essentially. Yeah. So again, so there is a to write down this formally, you need to somehow work out the axioms that somehow the image of a tensor product is isomorphic to the tensor product of the images, and these isomorphisms behave naturally, and so on. So essentially, it just means that, yeah, it is compatible. So the unit is mapped to the unit. So exact, yeah, it's clear. So exact is a functor between abelian categories. So if you have an exact sequence of Q Hodge structures, it stays exact, yeah, because morphisms between Hodge structures, they are somehow uniquely determined by viewing these Hodge structures as Q vector spaces. So this also means that the functor is faithful. So faithful means that it is injective on Holmes. Injective on Holmes. That is, if you have so somehow two objects and the home space, so this home between two objects is a Q vector space, so it is mapped into the home between the images of these two objects. So this map is injective. Yeah. So this is quite obvious, actually, here for the Hodge structures. So this data is called a neutral Tanakian category. So this category, such category with all these properties, and a fiber functor is called a neutral Tanakian category. Yeah. So.
What would be the base of the fiber in general? Also vector space is the base instead of two vector spaces.
So if you want to consider in general Tanakian category, so there should be some field, yeah. So they are k linear, where k is a field. So yeah, map into k vector spaces. Okay. So. Right, so so this pair is a neutral Tanakian category. And then there is a theorem that if you have yeah, a neutral Tanakian category, so let's go it's C, yeah, and the fiber is omega also, the fiber functor. So it is equivalent to the category of G representations for some yeah, so what is neutral? So I think that, well, it doesn't, it's nothing. So it's somehow, I won't be talking about this theory in general. It's just the name, yeah, so such category, so this okay, so it's a name of this type of categories, okay, neutral Tanakian. So you may consider more general Tanakian categories. So for example, the fiber functor is not always defined over the same field, but may be defined over a field extension, yeah. So I won't go into this, yeah, so my Tanakian categories will always be just like this, right? So the fiber functor is always defined over the same field as the category. And yeah, so I just want to say, yeah, I guess here also I need to, well, assume that, so this is over K. So C is K linear, and the characteristic of the field K is 0. Yeah, so also something that I will always assume, yeah, that the field is of characteristic 0. And then this is equivalent to a category of, well, let's write more exactly, of a finite dimensional representations of an affine group scheme over K. Okay, so affine group scheme. So basically, so this is the spectrum of some Hopf algebra. So we have talked about this Hopf algebras last time, yeah. So this G is the affine group scheme. And why is it not just, why is it a group scheme, not just an algebraic group? So actually it is not really what people usually call an algebraic group, because it can be something like this kind of infinite dimensional. So this G is a pro-algebraic group, actually. So G is a pro-algebraic group. So it is a projective limit of algebraic groups of finite type. Okay, and also, Right, so that is actually our Mumford-Tate group. So in the case, so if I apply this to Q Hodge structures with the fiber functor, then so this G is the Mumford-Tate group. So let's write it like this: Mumford-Tate of Q Hodge structures. So this is the absolute Mumford-Tate group. So our category is equivalent to the category of representations of this group, of the group scheme. Also, actually, I would, so this works in general for arbitrary Hodge structures, but I would like actually to consider the case when they are polarizable, because it is easier, and I will always work with polarizable Hodge structures because they are Hodge structures of oncohomology on projective varieties. That is what I want to consider. So I would consider also the category of polarizable Hodge structures. So what is it? Well, it's a full tensor subcategory. Yeah. So I just take those Hodge structures that admit a polarization, and I take the full subcategory, meaning that so the Homs between the objects are the same as Homs in the category of Q Hodge structures. So the category, the full tensor subcategory of polarizable Hodge structures. Then, in this case, we know that all polarizable Hodge structures are semi-simple, and then the Mumford-Tate groups are reductive, and also this is true about this absolute Mumford-Tate group. It will be MT of QHS polarizable is pro-reductive. So it is a projective limit of reductive groups. So why is it actually, so let's say a few words about how actually to construct this group, the absolute, so in general, I didn't give this definition. So for a general neutral Tanakian category, or Tanakian category in general, so this group is called the fundamental, the Tanakian fundamental group of this category. So this G is the Tanakian fundamental group. Of C omega, Tanakian fundamental group. So how is this group constructed roughly? So how to construct the Tanakian fundamental group. So the idea is the following. We'll look at this fiber functor. So we have the fiber functor from C into K vector spaces. Well, we may consider the group of automorphisms of this functor. That with this sign of the tensor product. So this is important. So they are automorphisms of tensor functors in the sense that these automorphisms should respect the tensor structure. More concretely, so what is an automorphism of a functor? So let's say we have, so these are automorphisms of omega as a tensor functor. So let's say we have some element here. So how to define what is an automorphism of a functor in general? Oh, the functor maps objects into k vector spaces. So an automorphism of a functor means that for each object here, I will have an automorphism of its image of the corresponding vector space. So for any x in C, I have gx, which is an automorphism. So an automorphism means what? It's an element of the GL omega of x. Yeah. So these are the vector spaces are, by the way, finite dimensional. Sorry if I haven't mentioned this. So this category k vector spaces are finite dimensional vector spaces. This gx to be an automorphism. So this collection of elements in this GL omega x should be compatible with all the structures. So first, it should be an automorphism of a functor. So it should be compatible with morphisms. So if we have a morphism from x to y, we'll look at the corresponding morphism between the vector spaces. And then we have these automorphisms here. So this diagram should be commutative. All right, so gy composed with omega f should be equal to omega f composed with gx. Okay. Then they should be compatible with the tensor structure. So we have tensor product of two objects, then this G, so compatible with the tensor structure. If we have two objects and we take the tensor product, then this should be the same as G x tensor product gy. Yeah, where somehow the omega of x tensor product with y is the tensor product of the corresponding vector spaces. And on the tensor product, we may act from the left-hand side by gx, from the right-hand side by gy. And also, well, we have the unit. Yeah, so this g of the unit should be the identity. But what are the the image of the unit is should be the unit in this category, which is the one-dimensional k vector space. So the question. So the automorphisms of this one-dimensional vector space are given just by k star. Yeah. So this g of the unit should be 1 as an element of k star, which is a gl of the one-dimensional vector space. Okay, so G should act as the identity on the unit element. Okay, and then so this is a group, and this group is actually the group of k points of some group scheme. So this is just a group. So all such things define. So you may take compositions of them. So if you have a bunch of such elements in GL omega x for each x compatible with everything, you may take compositions, and then you'll get another element of this group. So this is a group, and it's actually a group of k points of some group scheme. Yeah, so to define the group scheme, you need somehow to interpret these automorphisms a bit more, somehow extend them to define a functor on the category of k algebras. So this was somehow here we work just with k vector spaces, but we may take a tensor product somehow of k vector spaces with arbitrary k algebras and look at this thing as a functor on the category of K algebras. And then this functor will be representable by some Hopf algebra. So this is the, and then the fundamental, Tanakian fundamental group is the spectrum of this corresponding Hopf algebra. But yeah, so somehow the key points are just these automorphisms that respect all the structures on our categories. So the key points of the Tanakian fundamental group. And it's a huge group in general. It's difficult to understand what it is, actually, the group. So our category of rational Hodge structures, it is equivalent to the representations of this group, but the group is huge. And to understand a bit better why actually it works, so let's do the following thing. So one useful thing that we may consider is actually to restrict to some smaller, restrict our attention to some smaller subcategory. So the subcategory that I would like to consider is just the following thing. So let's take one polarizable Hodge structure. So I actually want to work with this category. So my Hodge structures will be polarizable from now on. So let's take one such Hodge structure. And let's look at the subcategory that this object generates. In which sense generates? We need to somehow construct again a tensor category with a fiber functor, somehow a Tanakian subcategory, a neutral Tanakian subcategory generated by this object. So let's denote it by V. So the tensor subcategory generated by V. Well, how to construct this tensor subcategory? So we need to, actually everything is semi-simple, so V decomposes into a direct sum of simple Hodge structures. But then we need also to allow tensor products. Yeah, so in the objects in this category are sub-Hodge structures of this tensor algebra. Yeah, so we need to take tensor products. We need to pass to the dual. So we may consider any sub-Hodge structure. I mean, a sub-Hodge structure in this case will be a direct summand. Actually, so we may say so they are direct summands in all these tensor powers of V. Well, and they are direct sums also, and they are direct sums. So sub-objects in this guy and the direct sums. And it is full, yeah, so full. So the morphisms between the Hodge structures are all the morphisms that we had in our category. Yeah, so this again is a neutral Tanakian category, so this category generated by V. But now, so let's understand what is the, let's think what is the Tanakian fundamental group of this subcategory. So the Tanakian fundamental group of this subcategory. So they are, well, at least let's again think about the K points of this group. Yeah, so so we have the restriction of our fiber functor to this subcategory. And well, let's take the sum G in the automorphisms of this fiber functor. Well, actually, so what does it mean? So this will give me such element gx for any object in my category. So in particular, I will have gv. Yeah. So this v itself is an object of my category. So I have gv here in glv. Well, from the conditions that I have, so I have not written here that it should be also compatible with duality. I'm sorry. Yeah. So the g of x dual is equal to gx. So I guess inverse of the transpose. Since my somehow the action of this g on objects of my category should be compatible with all operations, it's clear that for this category generated by v, so the action of this g is uniquely determined by the action on the object that was the generator. Yeah? Because all the objects of my category are obtained by what process can I use to construct the objects. I may take direct sums, direct summands, tensor products. Yeah. So starting and duals. So starting from v, so from here, so I automatically get the action on v dual. I automatically get the action on all tensor products, and on the direct summands. So this gv uniquely determines g. So gv uniquely determines g. So moreover, so now let's say we have some Hodge element of by degree 0, 0. So let's take x, which is in TV, well, intersected with TV 0, 0. So this Hodge element of by degree 0, 0. So what does it mean that we have this element? That means that we have an embedding of this identity. So this is the unit of our category into TV. Yeah. So the unit here goes to x. So that's an embedding of Hodge structures. And I know that G actually, so this G acts as the identity on the unit element. Yeah, so here this action of G on this Hodge structure is trivial. So G Q of 0 is 1, a multiplication by 1. So this means that this G V, yeah, and this G on the identity, so somehow how do I induce? So the action is induced by the action of GV, and I know that it should act as the identity on this sub-Hodge structure. This means that GV is in the stabilizer of X inside TV. Yeah. So this guy stabilizes all Hodge elements of by degree 0, 0. And as I mentioned, that is the definition of also one of the characterizations of the Mumford-Tate group, that it is exactly the stabilizer of all such elements. So this GV belongs to the Mumford-Tate group, or more exactly to the group of its rational points. So that's a rational point of the Mumford-Tate group. And conversely, given some element of the Mumford-Tate group, I will act by this element on all the tensor powers, and since so this action is compatible, so this will define a system of compatible actions on all the objects of this category. So conversely, given such a rational point, I can define the automorphism of this fiber functor. So the conclusion is that actually this omega is the same thing as the Mumford-Tate group, or more exactly the group of rational points of this MTV. So So the Tanakian fundamental group of my category generated by one Hodge structure is the Mumford-Tate group of E. So that's another definition, yet another definition of the Mumford-Tate group. Yeah, so you may just say that it is just this, somehow using this theory of Tanakian categories. Okay, so that's the this perspective from the so very briefly, just very briefly, the perspective that coming from this general theory of and general Tanaka duality. Yeah. So any questions about this?
So it automatically rejects the bigger default
Yeah.
fundamental projection.
Yeah, right. So it will be just somehow the representation will be given just by the projection from this big group to this guy. Empty Q Hodge structures, well, polarizable, will project onto the empty V, which is inside GLV, and that is the representation that defines the action of this guy on V, and it defines the Hodge structure.
I'm just wondering why you couldn't take the inverse limit. So what was the problem with that?
I don't think that it's actually it will work. Somehow, what you really need is to do all these things carefully. So you need to make sure that when you are taking this inverse limit, that you are compatible with all morphisms, right? And not only the inclusions, but all morphisms. I don't think that this. Okay, so in the case of the polarizable Hodge structures, maybe it will work. Actually, if you work this out somehow naively, because it's not. It's not really clear to me that in general. Okay, so just for a general category, I'm sure that this won't work. I guess maybe for the polarizable Hodge structures, you might just adopt this naive definition with the inverse limit. Because you see, so I mean, you really need to work out what happens if you have a morphism between the two Hodge structures. So you would like to construct a morphism from in the opposite direction between the Mumford-Tate groups. Yeah, and make sure that when you take this inverse limit, that everything is compatible with all such morphisms. Okay.
But like you take the smaller category at the level of morphism, where you allow only inclusions as morphisms, and then you go.
So this will. I don't think this will give the right answer actually in the end. Okay. Right. So also note that, for example, one thing that is obvious here is that you really have to take care of this, for example. Yeah. In this inverse limit, that you have to impose this condition, right? So that in your group, that you construct that somehow it is compatible with everything. No, I don't. I guess there might be a different construction, a simpler one in some cases, but in general, it works like this. So. Okay, so more questions, no? So actually, so one category that I want to talk about is yet smaller than this one, so the polarizable Hodge structures. So I would like to say a few words about the Hodge structures of abelian varieties. Let's the Hodge structures of abelian varieties. What it is. So that's also a full tensor subcategory. So Q Hodge structures abelian, full tensor subcategory of QHS polarizable generated by H1 of Q, where A runs, A are all abelian varieties. So generated, and maybe also I would like to add, and the Tate Hodge structures I would also like to have in this category, so let me put them here explicitly. Although they will appear so automatically when you generate actually by the abelian varieties, they will somehow arise as direct summations automatically, but let me put them here just to emphasize. So the abelian varieties, right? So the projective varieties, complex projective varieties by holomorphic to Cn modulo lattice and H1 of AC, so it has only two components, yeah? So 1, 0 and 0, 1. And then I generate, so I take tensor products and duals and generate everything by such Hodge structures. So what can we say about the Mumford-Tate group? So there is just one, actually, I mean, there is a lot we can say about the Mumford-Tate group, and people have studied this in detail. So the relation between the Mumford-Tate group and, well, it is, of course, somehow it is related, obviously, to the endomorphisms of these abelian varieties. And then there is, there are somehow classifications of algebra that can arise as endomorphisms of simple abelian varieties and so on. So, but I don't think that I will spend time on this. So what the one thing I want to explain is the following. So I would like to somehow, I mean, there is a question. So if you have given a Hodge structure, just arbitrary Hodge structure, just say on the homology of some projective variety that you like most, does it belong to this subcategory or not? Yeah, so it's not clear actually, yeah? So because when you take these tensor powers and tensor products and direct summations, well, some Hodge structures appear that are not really of this form, and they may be quite complicated. So how to distinguish actually this abelian case from the non-abelian case? So there is one way I know, I'm aware of. So let me explain this. So that's the Mumford-Tate group. So let's look at the Mumford-Tate group of our Hodge structure. So let's say we have this Hodge structure. So let's say this is V of A with rational coefficients. So we have the Mumford-Tate group of V. And we have its Lie algebra. So let's write MTV like this. So this is the Lie algebra of the Mumford-Tate group of V. It is, of course, inside the Lie algebra of GLV. And it is a sub-representation, yeah, of the Mumford-Tate group. So it is a sub-Hodge structure inside. So this GLV is what? It's just V tensor V dual. And in this V tensor V dual, which is a Hodge structure nature, there is a sub-Hodge structure, right? So this Lie algebra is a sub-Hodge structure. But let's look at the Hodge types of the elements there. So we have, so actually, of this guy. So what do we have? We have V tensor V dual. So in V we have 1, 0 plus 0, 1. And we take the tensor product with V dual, which has types -1, 0 and 0, -1. So what we will get when we take this product, so 1, 0 minus 1, 0 will give 0, 0. So this guy with this one will give, so 1 minus 1 plus 0, 0, yeah, and plus minus 1, 1. So these are the only possible Hodge types of the elements of this Hodge structure. Actually, on this one also. Yeah. So as Hodge types. 1, minus 1, 0, 0, and minus 1, 1. But now, let's observe. So there is an observation here. That if we have a Hodge structure in this subcategory, then the same will be true. So the Mumford-Tate group of any Hodge structure is naturally, so the Mumford-Tate group is always also a Hodge structure, naturally. So the Mumford-Tate group, it doesn't matter here which Hodge structure I have considered. So just, let's say it's just a Q vector space with a Hodge structure. So there is a Mumford-Tate group, and there is its Lie algebra, which is a subalgebra of this GLUE. So GLUE is a Hodge structure, always, yeah. And this is a sub-representation of the Mumford-Tate group. Therefore, it is a sub-Hodge structure, right? So as we know. So this, the Lie algebra of the Mumford-Tate group always carries a Hodge structure, okay? Naturally. And the claim is that so let's call it a proposition. So let V be in this subcategory of Hodge structures generated by abelian varieties. And then the Hodge structure on the Lie algebra of the Mumford-Tate group has or may have only Hodge types minus 1, 1, 0, 0, 1, minus 1. Well, why is this? Actually, it's almost obvious. Yeah. So, actually, it already follows from what I have said. So let's say that we have this Hodge structure. We may assume that this V is inside the tensor algebra of some W, where W is H1 of some abelian variety. Because this V is constructed by this taking the tensor powers and duals, and direct summands, but then you may take all the abelian varieties involved in this. It's a finite process, yeah. So you start from some finite number of abelian varieties. You may take their product and call it A, yeah, and then you do the tensor constructions, which means that you are inside this tensor algebra. And then actually, so I have already explained that in this case, so this is a representation of the Mumford-Tate group of W, and V is a sub-Hodge structure. So from here, we know that the Mumford-Tate group of W surjects onto the Mumford-Tate group of V. Yeah, because the Mumford-Tate group, so the sub-Hodge structures here are sub-representations of the Mumford-Tate group. And how do I obtain the Hodge structure on V? So the Deligne torus is just inside the Mumford-Tate group, and I act by the Deligne torus. This means that this Mumford-Tate group of W surjects onto the Mumford-Tate group of V. Yeah, and that is a morphism. If I look now at the level of the Lie algebras, this will define a surjection of Hodge structures. So this is a surjection of Hodge structures. Okay? But now W is just H1. Yeah, so about H1, I know that there are only components of these three types. So in the image, I also can have only components of these three types. So from here, I have the claim. So that's the end of the proof. Actually, it may be a trivial observation, but it was somehow that's maybe not so obvious from the beginning then, because if you look at this, subcategory generated by all abelian varieties, in general, what can you say? A priori not clear. So that's a very explicit thing, and it's very nice because it is actually easy to check sometimes whether this condition holds or not. For the, at least you may consider some groups that may arise as Mumford-Tate groups of varieties, for example, of hypersurfaces in Pn, and look at the Hodge structures. And then, well, sometimes you know that for some hypersurfaces you actually may say a lot about the Mumford-Tate group. Actually, generically, it will be as big as possible. And then you may just compute the Hodge structure on the Lie algebra of the Mumford-Tate group and check whether this holds or not. So, for example, let's do an example. So first, let X be a K3 surface. More explicitly, if you want, just a quartic in P3. A smooth quartic in P3. So smooth hypersurface of degree 4. Well, then the canonical bundle is trivial by adjunction. And we have H20 equal H02 equal 1. So in the decomposition of the H2, so what we have, H20, H11, H02. So this is one-dimensional, this is one-dimensional, so this H11 will be 20-dimensional, which is easy to compute for a hypersurface. What can we say about the Lie algebra? About the Mumford-Tate group. So let's say, so now my Hodge structure is this rational cohomology of the K3 surface, and I have a polarization. I have actually an intersection form. So the polarization. The polarization on the primitive part of this cohomology is induced by the intersection form. But, well, let's just write that we have, so V tensor V goes to Q of -2. So this is the intersection product. And it is symmetric, yeah, so. And well, let's say the Hodge group, right? So I would like to, so let's consider the Hodge group, actually. So the Hodge group, so we have the Mumford-Tate group of V, and inside of it we have the Hodge group of V. I recall, so the Hodge group is the same thing, but so the Mumford-Tate group is something generated over Q by the image of the delimitors. And if you consider a smaller subgroup, inside the delimitors you just have the circle, yeah, the circle U1. If you generate the Q, the minimal Q subgroup generated by the image of this circle, this is called the Hodge group. So in this case, the Hodge group is, so this will be called psi. So this is a subgroup of, so the psi. Let's look at the Lie algebra and let's determine. So actually, if we look at the Lie algebra, so the Mumford-Tate group and the Hodge group, they are almost the same. They differ by the center. So the Mumford-Tate group, so the Lie algebra of the Mumford-Tate group is actually the Lie algebra of the Hodge group plus just the center. So this is Lie of the Hodge group, and this is so the center of GLV, small GLV, right? And then, so what can we say about the Hodge structure on this Lie algebra of this Hodge group? So it is contained inside the SOV psi. So let's try to understand. So this SOV psi, so what is the Lie algebra of the orthogonal group? They are skew-symmetric. You may think about the elements as of skew-symmetric matrices, yeah? So this is isomorphic to the exterior square of V, right? So, but to, so as Hodge structure, so this will be of weight 4, so I need to twist by 2. All right. So let's try to understand now the Hodge structure on lambda 2V. Lambda 2V. So I take the, so I just look at this now and take lambda 2 of this guy. Yeah. So lambda 2V so has components of Hodge type. So so lambda 2V tensor C, let's say. So what will it be? So lambda 2 of H20 is 0 because this is one-dimensional. So then we'll have H20 tensor product with H11 plus lambda 2 H11 plus H20 product H02 and plus H11 tensor product with H02. So this will be of type 3, 1. So this will be of type 2, 2. Yeah. And this will be of type 1, 3. And then we twist by 2, so we have to subtract minus 2. And then this guy will have components of Hodge types, 1 minus 1, right? So we subtract 2, 2. 1 minus 1, 0, 0, and minus 1, 1. Yeah, exactly as for abelian varieties, the same thing. Well, I mean, somehow we don't know that the Hodge group is equal. Yeah, generically it will be equal. But still, yeah, so we observe that actually we are in this situation when we have the same type of Hodge decomposition on the Lie algebra of the Mumford group. And indeed, one may prove, so this I will do next week, as a special case, well, actually, yeah, so as a special case, maybe of some more general statement about hyperkähler manifold, that this Hodge structure is abelian. It belongs to the subcategory generated by abelian varieties. So this is called the Kuga-Satake construction. Okay. And also, well, just immediately, let's observe. So what is our computation? What is it based on? It's based on the fact that this is one-dimensional, right? If it were bigger, I would obtain lambda 2 of H20, which is of Hodge type 4, 0, yeah? So it would give me a Hodge component which may not actually appear in the category generated by abelian varieties. That's also actually useful. So let's write this down. So if we have a hypersurface in P3 of degree bigger than 4, so now X in P3 a hypersurface of degree bigger than 4, 5 at least. Well, then we'll have this H20 is actually greater than 1. And then in the, so this Hodge group of V, well, again, everything else works the same way, yeah, so that's also, yeah, so the degree 2 homology of any surface, it has the intersection product, and then our Hodge group is inside the orthogonal group of this intersection product. All right, so actually everything works, but well, the Hodge group is inside the orthogonal group, but so this guy has Hodge types. So 4, 0 minus 2, 2 will be 2 minus 2, yeah? 1 minus 1, 0, 0, minus 1, 1, and minus 2, 2. So these guys appear here that are not expected, yeah, for the abelian varieties. And actually, you may ask yourself, so if we, well, if this Hodge structure, yeah, so this V is the Hodge structure on the cohomology of a surface. Well, if we knew actually that the Hodge group was big enough, or that it was equal, for example, to this orthogonal group, then we could claim that we have already constructed an example of a Hodge structure which is not in this abelian category, yeah? Somehow geometric one. So, I mean, just an abstract Hodge structure, you may just construct somehow for a generic Hodge structure on this vector space with these fixed Hodge numbers, this will be satisfied. I guess I'll yeah, be talking about this somehow classifying spaces of Hodge structures next week also. But then it is clear that the for an arbitrary Hodge structure, somehow for a generic one on this vector space, the Hodge group will be as big as possible, and then you have an example of a Hodge structure that does not belong to the category generated by abelian varieties. But also, if we knew that this could be realized on the cohomology of some surface, it would give also a geometric example. Yeah, so why is it interesting? Well, because so if X has a big Mumford-Tate group, so big, then this H2 of XQ does not belong to this category of Q Hodge structures of abelian type, yeah? Well, this actually tells you something about the surface geometrically, maybe. For example, you may not have a surjection from a torus, an abelian variety, onto this surface, because if you had one, then you could pull back and this H2 would be embedded into the cohomology of an abelian variety, H2, yeah? So note actually that for an abelian variety, so HK of an abelian variety, yeah? So it is in the category generated by the Hodge structures of abelian varieties, because this is just lambda k of H1, yeah? So all cohomology groups in all degrees of an abelian variety are abelian, clearly, yeah? And so if you would have a map from an abelian variety onto X, you would pull back, the pullback would embed the H2 of your surface into H2 of an abelian variety, which contradicts this claim that it does not belong. So it's interesting to understand how to, well, how to guarantee that your variety has somehow has a big Mumford-Tate group, because it gives you some geometric information. So how to guarantee that the Mumford-Tate group is big? It's difficult to construct somehow explicitly, maybe such a thing. So what I would like to explain is somehow how one may view that generically in families of varieties, you would have a Mumford-Tate group would be as big as somehow as is reasonable to expect, let's say. Okay, so yeah, guys. So any questions about this thing with abelian Hodge structures? So just to summarize once again, so we have this definition of the Mumford-Tate group. Yeah, so we have several ways to view it, either as something coming from the abstract theory of Tanakian categories, or something more explicit as stabilize or fall Hodge classes of by degree 0, 0. And so now we have looked at the Hodge structure on the Lie algebra of this Mumford-Tate group and observed that actually it carries some interesting information. So the plan is that now I want to talk a bit about the behavior of Hodge structures in families. So about the variations of Hodge structures. So first, let's recall again the geometric construction. So how do we construct geometric variation of Hodge structures? It comes from a family of, let's say, projective varieties. So let's talk a little bit about families of projective varieties and, in relation with the behavior of the cohomology. So essentially, everything works the same way as I have sketched at the first lecture. So at the first lecture, we have recalled a little bit how Hodge theory works, classical Hodge theory. And in families, it works essentially the same way, but there is one essential thing to be added. So this essential thing is called Griffith's transversality. So essentially, so the variations of Hodge structures. So essentially, you just do the same Hodge theory, but over a base now. So, so what is a family of varieties? I'll just assume that I have a map pi from X to some base. So XB are complex manifolds. Pi is a submersion. Okay, so this means that the fibers of pi are smooth, complex submanifolds. And these fibers are the varieties which I want to study. Also, well, the B is connected. Yeah, so B is connected. So this is one family, not several families. Right, and then I want the fibers to be projective. I may just assume that this is embedded into Pn times B, and this commutes with the projection on the second factor. Yeah, so the fibers will be subvarieties in this Pn. Then I may look at the, instead of the cohomology of one variety, I'll look at the family of cohomologies of the fibers. So they are somehow, they form naturally what? The RK pi lower star of Z. So they form a local system over B. Yeah, so this is the sheaf whose fibers are cohomology groups in degree K of the fibers. So this is a local system over B. And on this local system, we have everything. Yeah, so we have the Hodge structures, our Hodge structures. So some more notation. So this XT is the fiber, the preimage of T, where T is a point on the base. So this is in the projective space. And the fiber of this guy over T is the cohomology group of the fiber. Cohomology group of the fiber. So let's try to understand the Hodge structures now. So how did we introduce the Hodge structures? We have looked at the de Rham cohomology of our manifold. So here we also have a de Rham complex, but relative de Rham complex. So the relative de Rham complex, for this I should start from this relative cotangent bundle, so of X over B, which is the kernel of co-kernel of the map. So the pullback of one forms on B go to one forms on X, and they go to relative one forms. So let's actually assume that the dimension of B is 1. And then we may take the powers, exterior powers of our bundles. So we'll have sorry, yeah, right, pi, exactly, thank you. Right, so what's the, yeah, so if you take the exterior product of this guy, it will surject onto the exterior power of this guy. It will surject onto the exterior power of this guy. And since this is of rank 1 in the kernel, you'll have somehow k minus first exterior power of this tensor, this one-dimensional bundle. And this fits into an exact sequence of de Rham complexes. Yeah, so this is the de Rham complex. This here is the relative de Rham complex. And here I'll have the pullback and the product with the relative de Rham complex with a shift by -1. Right, so in degree k, I'll have k minus 1, omega k minus 1. Okay, so the relative de Rham complex is quasi-isomorphic, just somehow. So let's think about the absolute situation. So when B was a point, then this was isomorphic to the quasi-isomorphic to the constant sheaf C. Right, so this will be quasi-isomorphic to the sheaf, which is constant somehow along the fibers. But there is also a holomorphic dependence along the base. So this sheaf is just the pullback in the somehow sheaf theoretic sense. So this pi minus 1 of the structure sheaf of B. So this is constant along the fibers and holomorphic somehow over the base. So to compute, so we have this local system. It is, of course, so if you mod the torsion, then this will be inside RK pi lower star C. Yeah. RK, so RK pi lower star C is a local system over B. So I want to make a vector bundle out of it. So let's take the tensor product of this local system with the structure sheaf. So this just means that I produce a vector bundle. So let's call this vector bundle VK, curly VK. And actually, so this thing by the projection formula, it will be the same as RK pi lower star of pi minus 1 of OB. Somehow when I have this RK, so I should think about this as the tensor product of the constant sheaf C and this pi minus 1, and then I can apply RK pi lower star to this C and remove pi minus 1 from here. So this is just the projection formula. And then, so this is the same thing as RK pi lower star of the relative de Rham complex of this guy. Good. So my vector bundle is now the push forward, the higher push forward of this de Rham complex. And so what do I have on this vector bundle now? So first I have the flat connection, because this vector bundle is just the bundle spanned by a local system. So so how to describe this connection? So on VK, we have a flat connection. So we may have, we may say that this connection just comes from this local system. So there are sections of this local system that are also sections of the vector bundle, and we may define that these sections are flat, yeah, and this defines a connection, a flat connection. But also we may we may so a flat connection nabla, yeah. So we may construct this nabla as follows. So let's apply. Let's look at this exact triple and apply the functor of the higher push forward to this triple. So this connection appears as follows. So RK, so from this star, from the sequence star, we have RK pi lower star of the de Rham complex. So this term goes to RK plus 1. So let me write this down again. So RK pi lower star of the relative de Rham complex goes to RK plus 1 pi lower star of the first term in this sequence. So pi upper star omega 1b product omega x over b with a shift, right? So here I can again use this projection formula. So this will be the same thing as omega 1b times the product with the RK plus 1 pi lower star. So this plus 1 and this minus 1 annihilate each other. So this will be the same thing as RK pi lower star omega x over b. So this is Vk, and this goes to, so this is omega 1b tensor Vk, where, so V, I put this, sorry, so I want to put this K below, so Vk. So this is my connection actually. So this connecting homomorphism in the non-exact sequence of higher direct images is the connection, the Gauss-Manning connection. Okay, so I have this vector bundle with connection. So what else do I have? So I have the Z structure on the somehow in the sense that this bundle is a complex, somehow a bundle attached to this local system of actually free abelian groups, and also I have the Hodge filtration. So let's recall, how did we define the Hodge filtration for manifolds when the base is a point? Well, we considered a truncation of this de Rham complex. We truncated in degree p. Yeah, so if we truncate the de Rham complex in degree p and take the, so define f p vk. So this will be R k pi lower star of the relative de Rham complex truncated in degree p So I take all the components of this complex starting from degree p. And then, so this will be by the same actually argument that uses the generation of the spectral sequence. So this will be a subbundle of VK, holomorphic subbundle. Yeah, so the bundle itself is obtained from this local system, but the subbundle is not. It's a holomorphic subbundle, and this defines the Hodge filtration. So the Hodge filtration on VK. So we have, so on VK we have the connection. So flat connection. Second, the Hodge filtration. Fp Vk is inside Fp minus 1 Vk, so the filtration is decreasing and finite. So what's the relation between the two things? So the relation is actually that the connection maps this Fp into Fp minus 1. So this is called Griffith's transversality. So why is this true? Again, from the same exact sequence star. So let's truncate this star and apply the push forward. So from star, so what will happen if I truncate in degree p? So I'll put p here, I'll put p here. So then I need to truncate this guy. Yeah, so truncating this in degree p, starting from degree p. But in degree p, what will appear is omega p minus 1, right? So omega p minus 1. So this, because of this shift, tensor product with pi pull back. Well, so truncating this guy in degree p is the same thing as first truncating this guy by in degree p minus 1 and then making the shift. So what I'll get is, here I'll get p minus 1. Yeah, and so here this is Fp. And we go, so replacing this dot by p minus 1. And where we arrive is Fp minus 1 Vk. Okay. Right. So the relation is called Griffith's transversality. So the if we restrict this Gauss-Manning connection to the subbundle Fp, then what we get is inside omega 1b tensor product with Fp minus 1. So Griffith's transversality. So nabla of FPVK is inside omega 1b tensor product with Fp minus 1 Vk. So this nabla cannot, so it does not preserve the filtration, right? So, but it cannot somehow spoil the filtration too much, only by 1. Okay. So questions, comments? So this is essentially the again. So we use this as the somehow motivation to define now. So what is a variation of Hodge structures? So it's all this data, but now without mentioning a family of project. Yeah. So there is also a polarization here. Yeah, because my varieties are projective. So actually we do have polarization. Let me first give a definition of them. Of VHL, no, well, let me just mention. So the polarization here comes again. So it's just there is a fibrous polarization because I have the I have the embedding into Pn times B. So on Pn, I have this bundle O of 1, which is, so the pullback from Pn of O of 1 to this guy is the relative O of 1 of the projection. And it defines the polarization on the fibers. So in terms of these local systems, what does it define in terms of the local systems? So the polarization on Vk is defined by a section of what? Of R2 pi lower star Z of 1. So I'll put the state twist here. So how does it work? Well, I have the here on X. Yeah. So I have Z of 1, and then this is the kernel of the exponential map from C to C star. And then I take the push forwards, right? So I take the push forward. So R1 pi lower star C star goes to R2 pi lower star this Z of 1. Okay, and so what I want a global section of this guy. Yeah, so the polarizations will be defined by the global section. So this global section, fiber-wise, will give a class in the cohomology in H2 of the fiber that defines the polarization. So how to get a section? I want a section of the local system of this R1 pi lower star C star, and actually I get one by just taking the first term class of the O of 1. So to here I have a map from H1 of curly X C star. Yeah. And here I have the class of the O of 1 on Pn. And so I just go there, and I have a kind of a relative first term class of the polarization on the fibers. So so this will define, again, so just like in the absolute case, so this will define a polarization, meaning such, let's say, sorry, so this is a polarization, so I'll write just, so let's say VB for the corresponding local system. So VB is this RK pi lower star of Z modulo torsion. So this is this local system which is written on the left-hand side. And there is this variation of Hodge structures on it, but from there we have a map into the constant local system over B with a weight minus K. Yeah. So, this is a morphism of local systems that defines fiber-wise a polarization. So a morphism of local systems that defines polarizations on the fibers. of pi. So here is the definition now. Abstractly, if we don't have a family of varieties, we may just consider such objects. So a variation of Hodge structures. Well, again, we may consider variations of Hodge structures that are Z local systems or that are local systems of Q vector spaces. So Z variation of Hodge structures over a base B is a Z local system so let's say VB. So this will mean that we have some, so local system, so with fiber, with a fiber of finite rank. That R for some R. And a filtration on V, curly V, which is VB tensor product with the structure sheaf of B. So this is a holomorphic vector bundle, and with a filtration as before, FP V inside FP minus 1V. So finite filtration by holomorphic subbundles, a filtration, so these are holomorphic subbundles. Such that fiber-wise we have this filtration defines a Hodge structure, and it satisfies the Griffith's transversality. So first is that for any t in B, so this VB, so the fiber over T with these bundles FP, so F dot, and the fiber of the corresponding bundle is a Z Hodge structure. We may define the Hodge structure in terms of the filtration by somehow taking the components of the filtration, intersecting with the complex conjugates, and defining this PQ decomposition this way, as we have seen on the first lecture. So fiber-wise it's a Hodge structure, and then we have this Griffith's transversality condition. So the second condition is that nabla of FPV is inside omega 1V tensor product with FP minus 1V, where nabla is the flat connection on V coming from this local system. Okay, so a polarization again. So formal definition again. So that the polarization is just that I have this amorphism of local systems that fiber-wise defines polarization on the fibers of these Hodge structures. So a polarization. So we may consider that now the category of polarizable variations of Hodge structures. And so, what do we want now to study? So the question is, how does the Mumford Tate group behave in such families? So we have a family of Hodge structures now. So it's not just any family of vector spaces with filtrations, but a little bit more. So we have this transversality condition. But then, in principle, it's quite flexible definition. Yeah, so we may construct a lot of such families. And the question is, how do the Mumford-Tate groups behave in families? To answer this question, so I wonder if I will be able to, yeah, I guess, well, let me at least define, yeah, so at least define the Hodge locus. So I'll finish today by defining the Hodge locus, and then next week I'll start by so finishing this discussion. So I'll explain well, how the Mumford-Tate group behaves. So I'll explain that somehow for a very general point of the base, this Mumford-Tate group is constant and does not depend actually on the point, well, up to the action of the monodromy, because to identify, well, it's somehow to identify the fibers over different points, we need to choose the isomorphisms, and they are well defined up to the monodromy action. But essentially, this Mumford-Tate group will be constant on the complement of some countable union of proper subvarieties of B. So what are these proper subvarieties of B? Well, just think about this definition of the Mumford-Tate group. Mumford-Tate group is a stabilizer of all Hodge classes, essentially. So then now, to understand it, we need to understand how many Hodge classes we have on the fibers in this variation of Hodge structures. Well, so we may apply the same thing, this tensor construction, to the variation of Hodge structures, and we may look at the Hodge classes of type 0, 0, yeah, at all points. At some points we'll have more Hodge classes, at some points we'll have fewer Hodge classes. But what do these loci where we have more Hodge classes, so what do they form? So this is the Hodge locus. Right? So let's try to understand this Hodge locus. So assume that we have this variation of Hodge structures over some base. Let's first look at this variation itself without applying this tensor construction. So what is the Hodge locus? Well, so we have B is a smooth manifold. We have this Z local system. With a variation of Hodge structures. So we have these subbundles. FPV. So let's think first about, we have the total space of our vector bundle. So what's the vector bundle? The vector bundle is just spanned by this local system. So the fibers are finite dimensional C vector spaces. So its total space is a fibration over the base. What are the Hodge classes? So the Hodge classes, they are, well, let's think about the integral Hodge classes first. So the Hodge classes, so in the fibers of this guy, so the Hodge classes are somehow elements of this local system. So if you think about the local system as of sub-abelian group in this V, so the elements are just points in this total space. So such point is a Hodge class when it is when it belongs to this local system and when it is of type PP. PP. So we have this F. Let's say F. FPV. So let's say that our variation of Hodge structures has weight K with a VHS of weight K. Right. So like in this previous example of homology, a cohomology of degree 2K. So let's say 2k, yeah, okay. So a Hodge class is an element of this local system which is also of type kk, yeah. So so let's try to describe the locus of such Hodge classes. So first, inside of this total space of V, we have the total space of this local system. Okay. So they are just these integral points, and V is spanned by this local system, meaning that so the fiber here is a C vector space spanned by a lattice. So point-wise we have these lattices, so we have a family of lattices, so they form some sub-manifold, yeah, so this is a sub-manifold actually. And then, so the projection to B is actually a covering map, because, yeah, you know, so if we have some element of this local system in one fiber, so this parallel transport, local parallel transport, will be some holomorphic so somehow some local submanifold that projects diffeomorphically to a neighborhood of a point in B. So this is a covering map, covering. So this total space of the local system forms the covering of B. Well, it has it's a covering. It's not connected. Yeah, so it has a lot of connected components. So let's write this as a disjoint union of connected components. So Wi are connected components of the total space of this local system. So we have a bunch of connected components covering our base. So the connected complex manifolds, countable union, actually. So we're interested in Hodge classes. So the Hodge classes should be points of this of one of these Wi's, and but they also should be of type kk. Yeah. So if we have a VHS of V2k, so a Hodge class is the same thing as an element, a point in one of Wi, such that, so let's say this point X in one of Wi, such that this point is also in well, in the Hodge in Fk, yeah, so in Fk V intersected with Fk V bar of type kk. But you see, so these points in Wi, so this local system, so it is stable under the complex conjugation. So if X belongs to Wi, X bar is automatically equal to X. So this holds if and only if X belongs to Fkv, yeah, intersected with Wi. So what is FKV? FKV is also, it's a bundle, so it also has a total space. So the total space of FKV is a submanifold, also submanifold. Okay, so now let's take this intersection, right? So, more precisely, yeah, so I should write the total space here. So let Zi be the intersection of the total space of Fkv with the connected component Wi. So one may say, so what can I somehow, how to say that the point somehow, the 2 points belong to the same connected component? One may say that these 2 points belong to the same connected component of this space if one can obtain one from the other by doing the parallel translation, yeah, parallel with respect to this flat connection. And then we'll look at all these points. So this somehow, this is a subvariety in the total space of V, right? A subvariety, a closed subvariety. It is an intersection of two smooth submanifolds that may be singular, nevertheless. But also, well, it is a subvariety of Wi. So actually, well, there are two possibilities, actually, mutually exclusive. So either this Zi now projects surjectively onto B, and then this Zi is actually equal to Wi. Or it does not project surjectively onto B. And then it is a subvariety of smaller dimension. So its image is of smaller dimension. And we define the Hodge locus as the union of the images of all such components that do not map projectively onto the base. So you see, so somehow what could happen? So this Wi is somehow a connected component of this local system, of the étale space of the local system, so to say. Yeah, it may happen that all points in this connected component are just of type KK. If this variation of Hodge structures was trivial, yeah, so it could happen that if my variation of Hodge structures has a summand of this Hodge state type, then this is exactly what happens. So all points of this Wi will have type KK. And then the intersection is equal to Wi, and it projects surjectively because it's a covering map. But it is not always the case. So sometimes some of these points in Wi are of Hodge type KK, sometimes they are not. And then the projection is not surjective. And so whenever we are in the situation when the projection is not surjective, then we take the union of all these things. So if the projection of this Zi is not, well, it is not equal to B, then P of Zi is in the Hodge locus. So I may take the union so I may look at all these components. So that let's call this in the Hodge locus. So this will be B Hodge of V. So this is the union of all P of Zi for all I such that P of Zi is not equal to B. Yeah. So this is for this one variation of Hodge structures for one local system V. And now I may take all its tensor powers, all these tensor constructions, and then I define the Hodge locus as the union over all EF of the Hodge loci for all, you know, this T EF of V. So let's VB, yeah. So let's put so VB here. So this is the local system. So this TEF is just VB tensor power E product with VB dual tensor power F. So I take all these tensor constructions. So I look at the same thing, so at all these components. So at the Hodge loci of all these guys, and then I take the union. So this is a countable union. So countable union. Countable union. Of what? Of images of closed subvarieties. In fact, the images will be closed also. Yeah, so that is an important point to make. So here, that I is a closed submanifold of the total space. That is obvious from the definition. But this map P is not proper, yeah, a priori. Neither the map P, nor the map, nor the restriction to the Wi. It's a covering, but it may have infinite fibers, this covering. It's not proper, so I cannot say a priori that I so that the image of that I is closed in B, and yet it is true. So I think that today I won't explain this, so that so let's take some time next week. So I'll go back to this question. Yeah. So I'll finish this discussion of the Hodge locus, and then of course somehow the Hodge locus is where I have some additional Hodge class. So look. Somehow, what does it mean that this component that I is not dominating? So this means that inside the image of this I, I have some additional Hodge classes. So if the component, if the intersection of Wi with FKV is equal to Wi, this means that this component consists entirely of Hodge classes. So these classes stay Hodge over all points of B. So this, they survive. So they stay Hodge type within somehow under so over every point of B. So in the entire variation of Hodge structures. And the other components are non-dominating, and so they define exactly the points in B where I have some additional Hodge classes. So these Hodge classes are exactly somehow the points of this Zi. So I want to consider the complement of this Hodge locus, and then to say something about the Mumford-Tate group of this complement, right? So that's my goal. So that is what I'll do next week. So I think that's it for today. Okay. So any questions, comments?
So it was essential that B is algebraic somehow, right?
So far it wasn't. So far, and I think it will not be essential for me. I won't be talking about the. And so it was essential that. Well, so far it was not really so essential that the fibers were algebraic. So the fact that the fibers are algebraic means that we have a polarization on these variations of Hodge structures. Not yet so important, but again, I will use this characterization of the Mumford-Tate groups as a stabilizer, so this I did for the polarizable variations. Yeah, so in general, I want to have polarizations. But the base may not be algebraic, it doesn't matter, maybe a disk, or maybe a polydisk, yeah, no problem. So far, everything works.
In the beginning of the discussion of the Gauss-Mann connection, you assumed that the base was one-dimensional.
Yeah, right.
Why exactly?
Yeah, so that.
After that, the definition there has nothing to do with the dimension of the base.
Yeah, right. So in general, you'd have, it's because, to prove this Griffith's transversality, you need to prove the same thing. So my proof worked only for the one-dimensional base. But then if you have a base of high dimension, then you just restrict to curves. Because you're Gauss-Mann connection, so you want to prove this.
Associated to that extension that you wrote, right?
Yeah, right. Yeah, so you can just, if you want, what you want to prove is this, so that for any tangent vector field, somehow you map FPV into FP minus 1V, and this means that you restrict a one-dimensional, you may restrict a curve, somehow one of the integral curves of the vector field. Use this argument, and then you'll get it for arbitrary base. Okay, so thank you.